Golden Iris Productions presents The Hidden Rhythms of the Hydrogen Atom, Wave Structure, Quantized Motion and Photon Emission by Mark F. Dennis. Part 1. Abstract. The development of modern atomic physics emerged from a sequence of foundational discoveries spanning the electron, proton, quantized radiation and matter-wave duality. Beginning with the identification of subatomic structure by J. Thomson and Ernest Rutherford, and culminating in Bohr's quantized atomic model, a new framework of discrete energy states replaced the classical continuous description of matter. Concurrently, Planck's resolution of the ultraviolet catastrophe introduced energy quantization through E equals h nu, later extended by Einstein's photon hypothesis, establishing the quantum nature of electromagnetic radiation. De Broglie's matter-wave theory further unified these developments by proposing that all matter exhibits wave-like behavior governed by lambda equals h over p. This work presents a consolidated historical and theoretical foundation of quantized atomic structure, emphasizing the emergence of discrete electron shells, standing wave conditions, and photon emission as interconnected consequences of wave-particle duality. Introduction. The discovery of the electron by J. Thomson and the subsequent identification of the proton through the work of Ernest Rutherford fundamentally transformed the understanding of atomic structure and established the foundation of modern atomic physics. Prior to these discoveries, the atom was widely regarded as an indivisible unit of matter. However, experimental evidence demonstrated that atoms possess an internal structure composed of charged constituents. Building upon this framework, Niels Bohr proposed his atomic model in 1913, introducing the revolutionary concept that electrons occupy discrete, quantized orbits around the nucleus. Within this model, electrons may transition between allowed energy levels, emitting or absorbing electromagnetic radiation, whose energy corresponds exactly to the difference between initial and final states. This provided the first successful theoretical explanation for the discrete spectral lines observed in hydrogen, and established that light emission from atoms is a quantized process rather than a continuous classical phenomenon. At approximately the same time, classical physics encountered a fundamental crisis in the form of blackbody radiation, known as the ultraviolet catastrophe. Classical theory predicted that a heated object should emit infinite energy at short wavelengths, a physically impossible result. In 1900, Max Planck resolved this paradox by proposing that electromagnetic energy is exchanged in discrete packets, or quanta, with energy proportional to frequency, E equals h nu, where h is Planck's constant, a fundamental constant of quantum mechanics. This result demonstrated that energy is not continuously divisible, but instead exists in discrete units.
Planck's hypothesis unexpectedly revived aspects of Isaac Newton's earlier corpuscular theory of light. Although wave theory had been firmly established in the 19th century through the work of Thomas Young and James Clerk Maxwell, Planck's quantization suggested that electromagnetic radiation also exhibits particle-like behavior. This duality was confirmed by Albert Einstein in 1905 through his explanation of the photoelectric effect, in which light is treated as discrete localized quanta, later termed photons. This established that electromagnetic radiation is neither purely wave nor purely particle, but fundamentally quantum in nature. Together, Bohr's atomic model and Planck's quantum hypothesis revealed that light is produced through discrete electron transitions governed by quantized energy exchange. This marked the beginning of quantum theory and fundamentally reshaped the understanding of physical reality. With light now understood to exhibit both wave-like and particle-like properties, physics entered a deeper conceptual transition. In 1924, Louis de Broglie extended wave-particle duality by proposing that matter, previously considered purely particulate, also possesses wave-like properties. This hypothesis is expressed by the relation lambda equals h over p, where the wavelength lambda of a particle is determined by its momentum p and Planck's constant h.
This proposal implied that every moving particle is associated with a wave, and for the electron, this wave-like behavior provided a natural explanation for the quantized orbital structure first introduced by Bohr. The Bohr model had already demonstrated that electrons in the hydrogen atom occupy discrete energy levels, or shells, labelled by the principal quantum number n. Each value of n corresponds to a specific allowed orbital radius. The ground state, n equals 1, defines the Bohr radius, a0, approximately 5.29 times 10 to the minus 11 meters, which sets the fundamental scale of atomic structure. Higher shells follow the relationship r sub n equals n squared a0, demonstrating that orbital radii increase rapidly with increasing quantum number.
What Bohr introduced as a postulate finds a physical interpretation through de Broglie's wave mechanics. The electron is permitted to occupy only those orbits in which its matter wave forms a standing wave around the orbital circumference. This condition requires constructive interference, expressed as 2 pi Rn equals n lambda n, ensuring that only integer wavelengths fit around the orbit. If this condition is not satisfied, destructive interference prevents stable orbital formation.
In this way, quantization merges naturally from wave behavior, rather than being imposed as an independent rule. This wave-based interpretation unifies Bohr's atomic model, Planck's energy quantization, and Einstein's photon concept into a single coherent framework. When an electron transitions from a higher to a lower energy level, its standing wave configuration changes, and the resulting energy difference is emitted as a photon, governed by E equals h nu. In this formulation, light arises from the reconfiguration of stable matter wave states. The hydrogen atom, therefore, represents the first physical system to demonstrate that matter and radiation are governed by the same underlying quantum principles, in which discrete atomic structure and discrete light emission are two manifestations of wave-particle duality.
Wave-particle structure, acceleration and velocity quantization. A direct consequence of the quantized shell structure of the hydrogen atom is that the electron's centripetal acceleration can be computed for each allowed orbit using classical electrostatic attraction. The electron experiences a Coulomb force, which provides the required centripetal acceleration for circular motion, expressed as an equals kq squared by mer squared n, where k is Coulomb's constant, q is the elementary charge, me is the electron mass, and Rn is the orbital radius associated with shell n.
Evaluating this expression at the Bohr radius n equals 1 yields an acceleration of approximately
A1 equals 9.04 times 10 to the 22 meters per second squared. This extremely large value reflects the strength of electromagnetic confinement at atomic length scales. As the shell number increases, the orbital radius scales as Rn equals n squared A0, leading to a rapid decrease in acceleration following an inverse fourth power dependence, An equals 1 over n to the fourth. This produces the sequence of discrete accelerations, A2 equals 5.65 times 10 to the 21 meters per second squared, A3 equals 1.12 times 10 to the 21 meters per second squared, A4 equals 3.53 times 10 to the 20 meters per second squared, and progressively smaller values for higher shells.
This behavior reveals a fundamental aspect of quantized matter. The electron is not simply moving more slowly in higher shells, but rather experiences a progressively weaker electromagnetic curvature of its orbit as distance from the nucleus increases. The ground state therefore represents the most strongly confined configuration, in which the electron's matter wave is compressed into its smallest stable standing wave structure. Higher shells correspond to progressively relaxed confinement and longer de Broglie wavelengths. This result establishes a direct correspondence between classical and quantum descriptions of the atom. From the classical perspective, Coulomb attraction provides the exact centripetal force required for orbital motion. From the quantum perspective, only those radii satisfying de Broglie standing wave conditions are permitted. These two constraints converge, selecting the same discrete orbital states as physically stable configurations.
Orbital velocity quantization. The orbital velocity follows directly from classical circular motion, where centripetal acceleration is related to velocity by a equals v squared over r. Solving for velocity gives v equals root ra. Substituting the quantized radius and acceleration yields discrete velocities for each shell. At the ground state, n equals 1, where r equals a0, the velocity is v1 approximately 2.19 times 10 to the 6 meters per second, corresponding to approximately 0.73% of the speed of light. This value is the standard Bohr ground state velocity and serves as a reference scale for atomic motion. For higher shells, the velocities decrease as v2 approximately 1.09 times 10 to the 6 meters per second, v3 approximately 7.29 times 10 to the 5 meters per second, v4 approximately 5.47 times 10 to the 5 meters per second. This leads to the scaling law, Vn equals v1 over n, which reflects a harmonic reduction of orbital motion with increasing quantum number. This inverse relationship arises naturally from the combination of radial scaling, Rn proportional to n squared, and acceleration scaling, An proportional to 1 over n4, producing a self-consistent velocity hierarchy.
Wave mechanical interpretation. The velocity scaling is not merely a classical consequence, but is directly linked to the de Broglie matter-wave condition. The electron wavelength is given by lambda equals h over mev, which implies that decreasing velocity corresponds to increasing wavelength. Substituting the quantized velocity structure yields longer matter wavelengths in higher shells, consistent with expanded orbital radii. This is constrained by the standing wave condition, 2 pi Rn equals n lambda n, which requires that an integer number of wavelengths fit around each orbit. Only those velocities that satisfy this resonance condition produce stable orbits. From the quantum perspective, momentum is restricted by the same relation, P equals MeV, and therefore by lambda equals h over p, ensuring that only discrete momentum, and thus velocity, states are allowed.
Ununification of classical and quantum descriptions. This framework demonstrates a direct equivalence between classical and quantum constraints on the hydrogen atom. The classical Coulomb force determines the allowable centripetal acceleration, while the quantum de Broglie condition determines allowable wavelengths. The intersection of these constraints produces the discrete set of stable orbital radii, velocities, and accelerations. Thus, the hydrogen atom emerges as a system in which classical dynamics and quantum wave mechanics are not competing descriptions, but mutually consistent conditions describing the same physical eigenstates from different mathematical perspectives.
To be continued.